Hello everyone, welcome to YouTube channel Energy-Exergy Theory Applications. I am Professor Tatiana Morosuk and I am the author of this YouTube channel. Today we're with the topic exergy. All lectures have a very dynamic style of presentation. Definitely some of you would like to learn more, particularly about exergy. We will be happy to answer your questions and provide with an extended information. Our contact email you can find in the description of each video. Please support our work with a like to this video, subscribe the channel, and share the link with your colleagues. Our next topic for discussion it is the application of exergy analysis to polygeneration systems. Polygeneration system, it is a general term that sometimes is used in publications. It can be cogeneration systems as a particular case of polygeneration systems or trigeneration systems. So this is not so important to specify at present. So we will discuss the energy conversion systems with more than one exergetic product. All discussions on polygeneration systems, let us start with the structure of these systems, what it means for us. So for cogeneration or for polygeneration system, it is in the middle of this figure. It is something abstract. Now, schematic is not so important. This system can use any kind of fuel, fossil fuel, and also renewables, including direct generation electricity from renewables. And outcome of cogeneration or polygeneration system, different energetic effects. For example, electricity, heat, and we can say refrigeration capacity. So thermal effect at the temperature below of the environment. In this moment, energetic efficiency or performance, it is the positive effects. As you can see now, it's plural, divided by driving energy. Driving energy, it is left block on this slide. And positive effects, we have some of thermal effects or work that can be generated. The same apply to driving energy because it can be thermal effect of combustion of any sort of fuels mentioned here, or work as a direct generation of work from renewable energies. So now let us proceed with the positive effects. This is the goal of our discussion. In the classical cogeneration system, always people discuss a generation electricity and heat. So such a cogeneration systems have absolute practical application and can be very large capacity and can be also small capacity. If two effects, electricity generation and thermal effect, together, then we can calculate energetic efficiency, and definitely energetic efficiency will be less than 1. So this is how always energetic efficiency is limited. However, if inverse thermodynamic cycle is included, and we will also consider electricity and refrigeration, or electricity, heat, and refrigeration, then we need to calculate the value of coefficient of performance, because energetic efficiency of such a polygeneration system, it's actually already trigeneration system, better to say polygeneration system, where inverse thermodynamic cycle is included and we have processes below of the temperature of the environment, then we need to calculate coefficient of performance, because this value very often will be higher than 1. And the last, if polygeneration system will also produce chemical products, how to include energetic effect of chemical products to the energetic efficiency. So means energetic effect of chemical products using the first law of thermodynamics. It is impossible to include these effects to the general equation. Therefore, energetic analysis for polygeneration systems is always problematic, and we cannot really rely on the provided results. Much better is to proceed with exergy analysis, because in exergy analysis we have quantity and quality of all effects. And we will write exergy balance, that exergy of fuel, it is exergy of product, exergy of destruction within all components of system, and exergy losses of the overall system. And now our interest, since we don't know schematic of polygeneration system, we will only discuss about fuel and product. Fuel can be, I repeat, any of these fuels mentioned on the slide, but products can be electricity, then it will be exergy of electrical energy, exergy of heat, exergy of cold, and exergy of chemical products. So we always have chemical exergy for any of chemical products. And the higher purity of this product, the higher will be, of course, chemical exergy. So through the application of exergy analysis to polygeneration systems, for us does not matter it is electricity, thermal effect above of the environment or below of the environment, or chemical product. We will start our discussions with the cogeneration system, where we have two positive effects, work and thermal energy. So according to the first law of thermodynamics, we are allowed to sum work and thermal energy, so power generated by system and heat rate, is two effects. And the driving energy, it is the mass flow rate of fuel, and multiply to lower or higher heating value, depends on the country where analysis will be conducted. As we know, in European school very often use it lower heating value, and in American thermodynamic school use it higher heating value. Both are possible, of course. So these three cogeneration systems based on open cycle gas turbine system, and we know that heat of combustion gases this heat can be utilized using different options. For example, the first option, we will put heat recovery on the way of combustion gases, and we will recover this heat and produce thermal effect. So this big red dot, it is thermal effect. We can also use combined cycle, open cycle gas turbine system, and steam power plant. Here is very simple schematic, but it is only principle. And a condenser, within condenser, we will generate heat much higher than environmental level. So condenser will not be dissipative component within condenser. Condenser can work at temperature 100, maybe even higher, with corresponding pressure, and we can generate thermal effect. Or we can use also combined cycle, and part of steam we can subtract from turbine and use the steam for generation of thermal effect. This schematic is very commonly used, and with different scale, large scale or small scale. And condenser within steam power plant is regular condenser. So then W net that will be generated by first schematic, it is so it is power that will generate within gas turbine system, and we will need a little bit power to operate pumps, but this value is very small, just to circulate working fluid. And for two other schematics, W net, it will be power generated within gas turbine system and within steam power plant. And also we will need work, so we need power for circulation of secondary working fluids, our heat, remove heat of condensation process, and also use heat that is subtracted from turbine. This part of steam subtracted from turbine to generate thermal heat capacity, or second thermal effect for cogeneration system. Now exergy analysis for the same three concepts of cogeneration system. So we have exergy balance of the entire system. Fuel is equal product plus destruction plus losses within the system, and exergetic efficiency, it is product, two effects, and divide by fuel. And now we need to find out what is fuel and also what is the losses for these three systems. So first of all, for the exergetic analysis, to start exergetic analysis, we need to discuss state zero. And we already know if open cycle gas turbine system is involved in any of cogeneration, trigeneration, polygeneration systems, and so on, air is coming from the environment, temperature and pressure of environmental air, that will be state zero for exergy analysis. And how many working fluids are involved in energy conversion system, so many state zero we need to calculate in order to proceed with the values of exergy streams, and after that formulate fuel and product for the overall system and for each component. So for all these three systems, exergy of fuel, it is exergy of air and exergy of fuel that is supplied to combustion chamber. Exergy of the product, it is a W net generated within gas turbine system. It is schematic 1, and schematic 2 and 3, it is W net generated within gas turbine system and steam power plant. And to calculate exergy of thermal effect, exergy of heat rate, we know that it is we can use this simple equation that showed us that exergy, it is the combination quantity and quality. Quantity, it is thermal impact, and quality, it is the so-called Carnot factor. We already discussed this equation several times in the earlier lectures on exergy analysis. And losses of the overall system. So these three systems. For system 1 and system 2, this is combustion gases emitted to the environment associated with losses of the overall system. And for the combined cycle with subtraction of heat from the a turbine, it is also combustion gases emitted to the environment, and depends on how we will treat condenser. If we will treat condenser as a productive component, then losses plus will be the difference of cooling media outlet and inlet from the condenser, but also we can treat condenser as a dissipative component. Then exergy destruction within condenser as a dissipative component will be charged to the exergy destruction of the overall system, and it will be no second term to contribute to exergy losses of this cogeneration system based on combined cycle. And now let us discuss two very complex cases. I mean complex from the point of view of calculations. It is polygeneration system when refrigeration effect is included, so cold exergy of cold or exergy of chemical products. So for these two cases in publications, sometimes there are results that difficult to understand because we need absolute clear description how authors are dealing with including exergy at temperature below of the environment and also exergy of chemical products. Now we will discuss this in detail. So the first system without chemical effect, only with refrigeration effect, it is polygeneration system because we will generate three effects simultaneously. So what do we have? We have three temperature levels: hot, environmental, and cold. And we have heat engine. As you can see, it is only thermodynamic concept. We have no real schematic. We have heat engine that will work in between two thermal reservoir, one thermal reservoir with the highest temperature level, but another thermal reservoir is with temperature higher than environmental temperature. So it means that we will generate a positive effect as thermal energy, probably for heating. Power that or work that we can generate within heat engine, we will not fully charge to net. Part of this work will be used for refrigeration machine. And within refrigeration machine, we have refrigeration effect. Let us assume we will cool down some products. And heat of the inverse thermodynamic cycle will be removed to the environment. And only the difference between work generated by heat engine and work required by refrigeration machine, that will be W net of the entire system. Therefore, for COP of as energy analysis, as a variable of energy analysis, coefficient of performance will be 3 effects: one, work, and two, thermal effects, but with different temperature level. One is above of the environment and another is below of the environment. So now exergetic analysis. Exergetic analysis equation logically will be the same. W net is the product, exergy of heat above of the environment and exergy of heat below of the environment, which is called cold. Or here in this equation, we have a more detailed explanation that exergy of fuel, it is exergy of high temperature heat source, product 3 effects, and losses, it is thermal energy removed to the environment from refrigeration machine. And one more time, for example, for such a abstract schematic, we have no real, no engineering schematic, only thermodynamic description. Exergy of two thermal effects, one is above of the environment, other is below of the environment, we can use the quantity and quality of energy. So quality, it is temperature level, and quantity, it is thermal effect. This trigeneration system that we discussed before, for example, we can convert to so-called heat-driven refrigeration system. Principle will be the same, but now we will a little bit change effects. Now heat engine will work from the higher temperature level to the environment, so there is no thermal effect, and all work that heat engine will supply, we will use for refrigeration machine. And in this way, as you can see, refrigeration machine is working using the mechanical work directly produced by heat engine. And there is no W net work that will be charged to the grid. For this heat-driven refrigeration machine, we have only one positive effect. It is refrigeration capacity. So fuel will be the same thermal so heat thermal effect at high temperature level, heat supply to the system, product only one effect, and losses will be exergy transfer to the environment from both from heat engine and from refrigeration machine. So as you can see, we always can convert polygeneration system. We will remove effects and we can change operation conditions, and we will convert polygeneration system to energy conversion system with only one positive effect. if this lecture was interesting for you, useful for you, can give you some ideas for your research, we will be very happy. And please support us with your likes for this video, subscriptions to the channel, and comments for this video. And of course, please share the links with your colleagues. Our next lecture will be dedicated to exergy analysis of polygeneration systems that are working below environmental temperature or crossing the environmental temperature. Thank you.